we will continue where we left off in the last class. So let us do a quick recap of what we were doing, and then we will go into the new things. So we were looking at deadlock free packet switching algorithms. To reiterate, what this means is that though the routing algorithm decides the paths through which packets will travel from one node to other nodes to the destination, we do need buffers in each intermediate node for storing and forwarding the packets. So we need to manage those buffers in such a way that we do not have a deadlock situation where every buffer has become full and we are not being able to forward packets because of the deadlock situation. So every node is locked. So in order to avoid that, we decided that one structured approach is we define a hypothetical graph called the buffer graph over the buffers that are available across all the nodes. So the pool of buffers available in all the nodes form the nodes of the buffer graph, form the vertices of the buffer graph, and there can be edges between two buffers if the two buffers are in the same node or in two different nodes, provided that there is an actual physical channel between those two nodes in the network, right. Then we showed that if the buffer graph is acyclic, then it guarantees that there is a deadlock free packet switching using the buffer graph. Another property, very important property that the buffer graph must satisfy is that corresponding to every path through which packets may be routed by the routing algorithm, there has to be an equivalent path in the buffer graph. Okay. So actually when the routing algorithm wants to route along that path, the packets are stored and forwarded along the corresponding path in the buffer graph. Okay. So we saw that there are only three types of moves that we need to be concerned about: generation, forwarding and consumption. Generation of packet at a node, forwarding to the next node, and consumption. We defined some terms like next buffer and first buffer. When a packet is generated for the first time, it is stored in the first buffer, and then it is for every position of the packet there is a designated next buffer to which it has to be forwarded. Then among these structured buffer graph based solutions, we looked at one scheme called the destination scheme. So here we assume that each node has n buffers, where n is the number of nodes in the network, okay, and we look at the set of buffers at the ith index in all nodes as one plane. So every node has n buffers, okay. So if we look at all the buffers with index 0 at all the nodes, then that plane, over that plane we define a graph which is a tree rooted at the node 0, okay. Similarly for all buffers which are indexed 1, we have a hypothetical tree with the sink as node 1, and at the ith plane we have all the buffers indexed I, and they form a tree which is rooted at node I, okay. Then we said that for all packets which must travel to destination I, we will first put them into the buffer in the ith plane and then move it along the tree on the ith plane, which takes us to the sink I, and that is how packets are delivered along the path. Now obviously this is deadlock free because packets travel from one node to another on a plane, and that plane is acyclic, it is a tree, okay. So there is no possibility of a deadlock in this scheme. Now today we are going to look at another scheme which is also buffer graph based. This scheme is called the hops so far scheme. So, the node U contains k plus 1 buffers. What is k? K is the longest length of a routing path in the network. So, among every vertex I and j, if we look at the routing paths, remember what is the set of routing paths that we were talking about? It was some P that we were talking about. P is the set of all possible routing paths in the network. Now, among all those routing paths, the length of the longest routing path is k, okay, and this scheme is going to work with k plus 1 buffers in every node. Now, if you compare k with n in the previous scheme, then k is less than or equal to n always, because routing paths never have cycles, right. So, the in the worst case a path can have all the n vertices, right. So, k is typically smaller than n. So, we are going to have a scheme which uses fewer buffers, and those buffers are indexed as, in the node U I have k plus 1 buffers indexed BU0 through BUK. Okay. It is assumed that each packet contains a hop count indicating how many hops the packet has made from its source. Okay. So, with every hop that the packet makes, its hop count increases. The buffer graph is defined by the graph Bg equal to B comma E, where B is the set of buffers on all the nodes and E is the set of edges, and where BUI BWJ belongs to E if I plus 1 equal to j and UW is an edge of the network. Okay. Now, that UW is an edge of the network is obvious, because we want to route only along the routing paths of the network, and this is interesting, that whenever we have an edge from one buffer in a node W node U to a buffer in node W, then this edge must satisfy this constraint, that I plus 1 is equal to j. Okay. What does that mean? That means that every time that the packet makes a hop, it rises one plane. Okay. So, let me show you an example, that suppose we have these 4 nodes, and let us say that a packet has to be routed like this. That is decided by the routing algorithm. Now, in this buffer management scheme, what do we have? We have k buffers in each node. Okay. So, 0 through k, all right. Now, when a packet has to be routed from this node U to the node V, okay, we will first put the packet here. Okay. Now, every time the packet makes a hop, it will not be copied from, it will be copied from BU0 to BW1. Okay. So, it is going to go from here to here. Okay. For the next hop, it will go from here to, let us call this Z, it will go to BZ2. Note that this index is increasing by 1 every time. Okay. And then when it goes here, it will go in BV3, right. So, not here, not here, not here, it will go there in BV3. Okay. Now, this is how the packets are routed. Is that clear? So, at the source it starts, it is put into the buffer 0, and then with every hop it jumps by one index, right. Now, how many buffers do we have in every node? K, what, k plus 1, and so if it starts in 0, then with k hops it can go to maximum the index k, right, and we know that the length of the longest routing path is k. So, every routing path is upper bounded by k. Okay. So, by the time it makes k hops, it will definitely reach the destination, right. Now, how do we show that this is deadlock free? In order to have a deadlock, we have to have a cyclic wait condition. So, we will have to have two buffer, at least set of buffers where every buffer is waiting for the next buffer to clear, right. Now, you see, you can have a packet which is sitting in a buffer I in some node, okay, it is sitting in buffer I in some node, and in the next hop where does it expect to go? It expects to go to buffer I plus 1 in the next node, right. So, it can wait for buffer I plus 1, right, but can buffer I plus 1 ever wait for buffer I to clear? No, because packets are always put into buffers of higher index in the next node, okay, higher by 1. So, a cyclic wait can never happen, because a higher index packet sitting on a higher indexed buffer can never wait for a lower index buffer to. Okay. So, by that we ensure that there cannot be any deadlock in this. Okay. Now, the next question comes is, we have reduced the number of buffers. In the first scheme it was n, in the second scheme it has come down to k, where k is the length of the longest path. Can we reduce it further? So, there is another scheme which is worth mentioning here. This is called an acyclic orientation based scheme. Okay. Firstly, we must understand what is an acyclic orientation. So, an acyclic orientation of a graph G is a directed acyclic graph which is obtained by directing all edges of G. Okay. Now, what does that mean? I have this graph, okay. Now, one acyclic orientation of this is this, where it is the same graph except that we direct the edges. So, and the important thing is that the graph should remain acyclic, there should not be a directed cycle in it, right. So, you see that in this graph there is no directed cycle. So, this is an acyclic orientation, okay. But this one is not an acyclic orientation, because we have a directed cycle here, which is this one, all right. So, this is not an acyclic orientation. So, this one is an acyclic orientation, right. Now, let us understand what this acyclic orientation has to do with the routing of packets. So, we want to make sure that the routing of packets through the packet switch network does not go in cycles, right. So, we want them to be acyclic, and also in order to prevent deadlocks, we want to make sure that they are acyclic, right. So, oh yes, you can always do that, because it is very easy to see. What you do is you create a spanning tree of the graph, right, and direct all the edges of the spanning tree towards the root of this thing, right, and for all the other edges make them downwards. So, you do a topological ordering of the vertices and then make all the edges pointing in the direction of the topological order. Right? That way you will always get an acyclic orientation. In fact, there are multiple acyclic orientations that are possible, and it is easy to see in this particular graph also. It is easy to see that we can create another acyclic orientation, not very hard to do. Right, this is another acyclic orientation. Okay, right. Now, let us see what we want to do in the routing algorithm. A sequence G1 through GB of acyclic orientations of G is an acyclic orientation cover of size B. Okay. Now, this is an interesting thing. We want to define something called an acyclic orientation cover. Okay. What does the acyclic orientation cover mean? We want to cover a collection P of paths. Okay. So, the target of the acyclic orientation cover is to cover a collection P of paths such that for each path pi belonging to P, we can write it as a concatenation of B paths pi 1 through pi B, where pi I is a path in Gi. Okay. Let me reiterate. I have B different graphs. Each of these graphs is a acyclic orientation of G. I am not saying that these are distinct. Two or more of these can be replicated also, but we will say that this collection of B graphs is an acyclic orientation cover for a collection of paths P if every path P can be written as a concatenation of B paths, okay, where we have pi 1 through pi B, where the ith path is in the ith graph. Okay. Again, these paths can consist of a single vertex also. It is not necessary that you have to have edges in each of these paths. All right. Okay. Let us see an example first of an acyclic orientation cover, then we will go into more generic case. So, I will start with a simple example of a ring. Okay. A ring. So, for a ring like this, suppose this is a ring. Okay. Now, I will create 3 acyclic orientations of this. So, first I will designate, I will pick up 2 vertices U and V. This is just I am doing it for something which I will refer to later. Now, the orientations that I am going to look at are these. This is one orientation. Okay, so this is acyclic because there is no directed cycle here. This is my G1. Okay. Let us look at another one. Let me first draw the graph and then I will put the directions. Okay, this is my G2 and this is G3. G3 and G1 are identical. Okay. Now, we claim that this is an acyclic orientation cover for the routing paths in this network. Okay. Not only that, we will make sure that every shortest path between any pair of vertices in the ring corresponding to that we have an image in this acyclic orientation cover, right. So, for every vertex which is, so if I choose some x and y where x is here, y is here, then I can route it in G1, okay. And when it reaches y, it just goes from y here to y here to y here. Okay. So, the paths in G2 and G3, remember that in the acyclic orientation cover, every path pi will have to be written as a concatenation of some path pi 1 in G1, some path pi 2 in G2, some path pi 3 in G3. So, the pi 1 is this path here, pi 2 is just this node, pi 3 is just this node. Okay. Now, if x is here and y is here, then how am I going to route it along the shortest path? What will be the shortest path? This one, right. So, how am I going to do it? I will, yeah. So, xu pi 1 will be only x, right. Pi 2 will be from x to u, and what will be pi 3? U to y. Okay. Similarly, if x is here and y is here, shortest path will be like this. How are we going to take that? First part here, okay, and from here in G2 we can route the remaining part, right, and in G3 we do not do anything at all. If you were to route from y to x, then you will take the first part in here, and then the second one you will take from here. Okay. So, what does this show? It shows that for a ring, okay, we have an acyclic orientation cover. No, it has to be strictly in this order. The concatenation of paths has to be strictly in this order. It is very important. You cannot do pi t, pi 2, pi 1, pi 3, no, that is not allowed. For a ring, we have an acyclic orientation cover of size 3, G1, G2, G3. Okay. With 2, you will not be able to route it through shortest paths. Okay, just convince yourself that with 2, you will not be able to support shortest path routing. You will be able to route from every node to every node, no doubt, but they will not be necessarily along the shortest path. Okay. Now, that is something that I request you to convince yourself and create a, create an acyclic orientation, two acyclic orientations of a ring, and then show that there is a shortest path which cannot be replicated in that set of 2 graphs. So, it is not an acyclic orientation cover which covers all shortest paths. Okay. But this with 3 we have. So, that what does that mean? That means, if you have a ring network, then with only 3 buffers in each node, you will be able to route the packets along shortest path. The question is, how do we guarantee that this routing along the acyclic orientation cover it guarantees that it is deadlock free. Okay, that is something that we have to prove. So, let us look at the generic algorithm, the methodology here. So, in general, we have a set of graphs G1 through GB of acyclic orientations of G. We call it an acyclic orientation cover of size B for a collection of paths P, if we can rewrite every path P as a concatenation of B paths, where pi I is a path in Gi. Okay. Now, that is clear, I suppose. Now, a packet is always generated in node U in buffer BUI. This is how the packet switching strategy is going to work. The packet is generated in node U in buffer BU1. In the first buffer, we store the newly generated packet. A packet in buffer BUI that must be forwarded to node W is placed in buffer BUI if the edge between U and W is directed towards W in Gi, and to BWI plus 1 if the edge is directed towards U in Gi. Now, what does this mean? What is the acyclic orientation cover? Let us come back to this ring network. It has 3 different planes, right? G1, G2, G3. Every path between a pair of vertices x and y was being replicated as a set of concatenation of paths in this, right. Now, the idea is that as long, so in the buffer network also, we have 3 buffers in every node. The buffers in plane 1 are following this graph, buffers in plane 2 are following this graph, buffers in plane 3 are following this graph. Now, if you want to go from x to z here, then in G1 it is in this direction only. So, therefore, the packet will go from Bxi to Bzi. We will not change plane. Why? Okay, right. Now, if you want to go from x here to u here. Okay. Now, see, you cannot go from x to u here in this plane, because now if we try to move the packet from bxi to bui, there is a potential of deadlock, because there may be a packet sitting in u wanting to go to x, right. So, when I want to send a packet from bxi to u, I will send it to bu I plus 1. Okay. I will move it to bu I plus 1. Yeah, let me explain this again. I am in a particular, the packet is there in u and in the buffer I of u. Okay, so the packet is currently here. So this is node u. Okay. Now remember that when we talk about an acyclic orientation cover, it is a set of graphs. Okay. Now I am in the bui, in the ith buffer. Okay. So I will look at gi. I will look at the ith graph gi. Now in gi, suppose this packet has to be forwarded, but the routing algorithm decides which is the next node to which it has to be forwarded. Suppose w is the next node to which it has to be forwarded. This is u. Now in gi, there are two cases, that in gi there is an edge from u to w. This is case 1. If there is a edge from u to w in gi, okay, then I am going to move the packet from bui to bwi. In other words, if it was in this buffer in u, then when it goes to w, it goes to a buffer on the same plane, as if it is moving along the edge of gi, right. And the case 2 is in gi, suppose it is the other way around, that in gi the edge is from w to u, because it is a orientation, right. The edge can either be in this direction or in this direction. Now if it is in this direction, then I will not move it from bui to bwi. I will move it from bui to is that clear? Now we claim that this is going to guarantee that this is a deadlock free packet switching algorithm. Now is it clear what the algorithm does? Because on the same plane you cannot route it along that graph, right. Now remember that every routing path, corresponding to every routing path, there is a corresponding concatenation of paths on the G1 through Gk. Okay. So if the packet is in u and it must travel to w, and this in this graph there is no path from u to w, no edge from u to w. There has to be an edge from u to w somewhere in the lower graphs, lower or higher, I mean gi plus 1, gi plus 2, gi plus 3, it has to be there, because there is a concatenation of paths which reflects the original routing path, right. So, in that corresponding path the packet will move from u to w, right.
If there is a path in let's say gi plus 1, then we should be forwarding it from bu I plus 1 to pw I plus 1 at that plane itself.
Now, see, the interesting thing is that we did bw I plus 1 here, right. Now, what we are not saying is that we are not saying that
Because the second plane may also not have
that is what I am saying, that the second plane that is gi plus 1 may not have the edge from u to w, okay. But we know that somewhere in gi plus 1, gi plus 2, whatever, there will be an edge.
it should be bu plus I plus 1.
Yes.
It should be from bui to bu I plus 1.
No, this is a clever optimization. You don't need to do that, right. All we want to guarantee is that there is no deadlock, right. See, all these hypothetical acyclic orientations and graphs and all that, what are we going to use it for eventually? We want to route packets from one buffer to some buffer in the next node. The next node is decided by the routing algorithm. The packet switching algorithm, the buffer management algorithm has no choice over the next node, that is decided by the routing algorithm. What we are trying to do is to manage the buffers in such a way that when we move it to a buffer in the next node, these moves do not lead to a deadlock situation. So, we will prove that if you move the packet from bui to bwi plus 1, we will still guarantee that there is no deadlock, okay. Now, if we can guarantee that, then fine, I mean why should we again go down 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 and then forward, that will only create extra number of moves, right. So, we will directly move from bui to bwi plus 1, okay, even if gi plus 1 does not have the edge in that direction. If it is supported in the current graph in gi, then we will just jump from I to I plus 1, otherwise we will just go to from bui to bwi plus 1 direct, okay, right. That is what we have to prove, that it will not create, alright. So, to prove that it is not going to create a deadlock, that is what we are going to prove now, okay, and that will convince us that this is going to work, okay. Right. So, let me write down the thing. So, the result is that if any acyclic orientation cover for P of size B exists, then there exists using only B buffers in each node, okay. So, let me start working on the proof. So, let GB be the cover. And for node U, the buffers are BU1 through BUB. Okay. We write UW belongs to what is this? This is the set of edges in GI. Remember, GI is a directed graph. So, it only has directed edges. So, UW belongs to EI if edge UW is directed towards W in GI. Okay. And otherwise, if it is in the opposite direction, then we will write WU belongs to EI. Now, because it is an acyclic orientation, for every edge either you will have UW belonging to EI or you will have WU belonging to EI. Okay. Now, the buffer graph is defined as follows, that BUI BWJ belongs to the buffer graph BE if and only if, let me write down the conditions for that, UW belongs to E and I equal to J and UW belongs to EI, or I plus 1 equal to J and WU belongs to EI. This is what we talked about, right, that we will have I equal to J, then if UW is in EI, then it goes from BUI to BWI, so I equal to J, right, in the buffer graph, or if WU belongs to EI, then it goes to from I to I plus 1. So, I plus 1 is J, right. These are the edges that are there in the buffer graph, right. We have to prove that this buffer graph is acyclic. Okay. How do we prove that this is acyclic? Right. So, we only have edges from a buffer I at level I to edges to either buffers in the same level or buffers in the next level, right. There is never any edge from a higher indexed buffer to a lower indexed buffer, right. So, that guarantees that this graph is acyclic, right. So, if this graph is acyclic and packets are only moving along the edges of this graph, so this is going to be a deadlock free controller, right. See, in a buffer graph controller, the main thing is to show that your buffer graph does not have a cycle, right, and the controller only follows the routes packets along the edges of the buffer graph, right. Now, if you only follow the edges of the buffer graph and the graph is acyclic, then obviously you cannot have deadlock. So, this is a simple philosophy behind all buffer graph controllers. How we construct the buffer graph and with how many few buffers we can do that is how the strategies vary. So, we first looked at a strategy with n buffers, then we looked at a strategy with k buffers where k is the longest routing path. Now, we are looking at a strategy which is b buffers and b is an acyclic orientation cover, which typically can be much smaller than the length of the longest path. Why? Because the longest path is actually going to get split into these b subpaths, right. So, the number of subpaths, it can be quite less than the length k, you know. Yeah. So, that is an intuitive way of doing it. Okay. There are graph theoretic algorithms to prove how many acyclic orientation covers you can have and all that. There is a section on acyclic orientation covers, how to determine them, how to prove that this is an acyclic orientation cover and things like that. Okay. So, for the ring, I showed you that you can have an acyclic orientation cover with 3 buffers, and that covers all the shortest paths between all pairs of vertices in the ring, right. In a tree, we can have a acyclic orientation cover with only 2 buffers. Okay. Let me give you an example. I mean, as soon as I give you the example, it will be immediately clear. Any questions on this result, that where we prove that if you have a acyclic orientation cover of size b, then you have a buffer graph controller which can work with only b buffers.
How is it necessary that size b will be always less than k?
No, it's not going to be more than k, because if it is more than, if you cannot find the acyclic orientation cover of, see, what you can always do is, if you have a small b number of graphs by which you can do the cover, then you significantly reduce the number of buffers. If you find that it is going towards k, then you can actually use the hop so far scheme, then you do not have to worry about acyclic orientation covers and all that. But typically, for most graphs, the size of the acyclic orientation cover is significantly smaller than the length of the longest path in the graph.
Every such graph will be able to make such a acyclic orientation cover.
Now, that's a graph theoretic subject altogether. How do you create acyclic orientation covers? Which types of graphs have how many? What sized acyclic orientation cover? How do you find the minimum acyclic orientation cover? Okay. So, that is a subject on its own. We are not going to go into that, because then we will have to learn a lot of graph theory. So, for rings, I showed you how we can get it. For trees, I will give you an example. Suppose this is a tree. So, this is a tree, right. Now, when I say that I am going to create an acyclic orientation cover of this, I will first choose one of these vertices, let us say this one, okay, and then I will create 2 trees. One will be an orientation where this is a sink, and other will be an orientation where this is a source. Okay. So, first let us create the one where this is a sink. So, that one can be something like this. okay, or R, and the other one is where this is the source. Right. Now, in a tree there is nothing like shortest path, there is only one path between every pair of nodes, right. So, suppose I want to reach from x to y, what am I going to do? I will follow this graph, this one up to R. When I reach R, from there I will take the, so I will go from x to R on this, and then from R to y on this one, right. How am I going to go from y to x? So, on this one I will come from y to R, and then from here I will go from this, okay. How am I going to go from x to z? So, I will choose this one. So, I will traverse along this up to this, and then take this one to z, right. So, with only 2 buffers in every node, we can have a deadlock free packet switching in trees, right. Okay. Now, what we have done so far is we have looked at all structured solutions. Structured solutions are where we have an underlying buffer graph in our mind, and that buffer graph, based on the structure of the buffer graph, because of the acyclic nature of the buffer graph, it follows that if we follow the edges of the buffer graph for switching the packets, then we are guaranteed that they will not deadlock, right. In the next class, we will look at some unstructured solutions, solutions in which we will not have any underlying buffer graph in mind, but we will still be able to route packets, guaranteeing that there will be no deadlock.